Hello guys, welcome back to my channel HK Official. Today I'm there with the second part of this video. We are in unit number 1 of wave optics in engineering physics. I have covered interference concepts in the first part of the video. I hope you have seen that video and understood it well. In this video, we are going to study the very most important part of the chapter, or we can say the unit, which comes in exam. So let's go ahead and reach out to it. The name of the topic is interference due to uniform thickness thin film. In this, we have to see a diagram, its labeling, its considerations, its derivation, and also the conditions for its maxima and minima, which we will see further. And the whole derivation comes in exam for around 6 to 8 marks. So it becomes a very important topic. So let's go ahead, and I hope you have learned in my last video what is thin film. Okay, so that is the application we are going to see in this part. So in these images, we can see the fascinating phenomena of interference occurring in thin films. Interference happens when light waves interact with each other, leading to constructive and destructive patterns. We have seen this concept in our first part. In the context of thin films, these patterns are formed due to reflection and transmission of light waves at different interfaces within the film. These images demonstrate the colorful and intricate patterns that emerge as a result of this phenomena. Let's break down what's happening step by step. You are seeing the diagram of this concept. So we begin with the monochromatic light ray that is incident at an angle denoted as I, related to the normal of surface. When this light ray encounters the surface of thin film, two things occur. First, a part of the light ray is reflected along a path marked as AE. This is our first reflected ray. Simultaneously, another part of the light ray is refracted as it enters the thin film along a path labeled A. This refracted ray then travels within the film until it reaches point B on the lower surface. At point B, this refracted ray is once again reflected, this time along path BC, forming our second reflected ray. Now, the key factor that gives rise to interference is the path difference between these two reflected rays. The ray that traveled through the thin film has covered a longer distance than the ray that was reflected directly from the top surface. This leads to a phase difference between the two rays. Depending on whether these phase difference results in constructive or destructive interference, we observe patterns of bright and dark regions where the waves are in phase and reinforce each other. We see regions of enhanced brightness. Conversely, where the waves are out of phase and cancel each other out, we observe darker areas. I hope you are clearing the concept. This phenomena of interference due to the path difference between the two reflected rays is what gives rise to the intricate patterns and colors we often see in thin films, like the vibrant hues on soap bubbles. Here I have written all the consideration points in the diagram. First point says like SA is the ray of monochromatic light incident at angle I to normal. Second says the part of the light get reflected along AE and the part of light get refracted along AB. Again from point B it get reflected along BC, then it emerged out. Interference caused due to the path difference between two rays. I hope you have understood what I have explained you in the last slide. The context in short I have written over here. This is the main formula from which we are going to derive the concept, that is geometrical path difference. We denote it as delta. It is nothing but the path traveled in the film minus path travel in the air. Now let's see how it is applied. Here I have kept the same diagram and the same formula. Geometrical path difference, that is delta, is nothing but path traveled in film minus path traveled in air. So in the diagram, see and let me know what is path traveled in film. Yes, you are right. It is AB and BC. So we will add AB plus BC in the path traveled in film. Now what is path traveled in air? Yes, it is AF. So we will minus it according to the formula. Now with the help of this, we will make out what is the optical path difference. Here we will just add the mu. And I hope you know what is mu. Mu is nothing but the refractive index of any medium. And mu naught is nothing but the refractive index of air. So the same formula is present, but before AB plus BC I have multiplied mu, and before AF I have multiplied mu naught. Mu naught value I hope you know that is 1, because the refractive index of air is 1. So just for the formula base I have written it. Now mark it as equation number 1. Now let's go further. Here, the first step of the derivation is that we have to find AB and BC. Why we have to find AB and BC? Because in the formula, the main which we have seen, the path traveled in film, is AB plus BC. So for that, we have to find AB and BC. So for finding AB and BC, we have to consider triangle ABG and triangle CBG in the diagram. So on every slide, I have put the diagram, so you will not have any confusion at all. So in the triangle, concentrate in triangle ABG. Now in the triangle ABG, we have to consider angle cos of R. So cos, we know what is cos, it is adjacent side upon hypotenuse. So concentrate on triangle ABG and see what is cos R. Cos R is nothing but BG upon AB. That's the same what I have written over here. Cos R is BG upon AB. Okay. Then from this only we know that AB will be equal to BG upon cos R. Now again see the diagram. The BG is nothing but the thickness of the film. So that is T. So I have substituted T in the place of BG. So AB becomes T upon cos R. Similarly, we will find out BC. Again consider triangle CBG. In that cos R is nothing but BG upon BC. Remember, adjacent side upon hypotenuse. So BC will be equal to BG upon cos R. Again, what is BG? Is nothing but the thickness of film. So we will replace it by T. So again, we get to know what is BC. It is T upon cos R. So we got the value of both AB and BC. I hope you are understanding till now very well. Let's go further. Now we have to find AF. In our first formula, what we have known? We know that path traveled in film minus path traveled in air. So for path traveled in film, we know what we have to find. We have to find AB and BC. We have find it out. Now in path traveled in air, we have to find AF. So for finding AF, we have to consider triangle AFC. In triangle AFC, you can see in the diagram, we have to find out now sine angle. Remember what you have to find. First step, we have to find cos angle. In the second step, while finding AF, you have to find sine angle. So keep it in mind. So sine I, we know what is sine is nothing but opposite side upon hypotenuse. So sine I in triangle AFC, what is it? It is AF upon AC. Okay, then AF will be equal to AC into sine I. Now see the diagram, and what is AC? AC is nothing but AG plus GC. Just substitute in the equation. So we'll get AF is equal to AG plus GC into sin I. Okay, I hope you understand this. We have find out AB, we have find out BC, and here also we have find out AF. Now we have to find out AG and GC also for substituting it again into the equation number 2. So for finding AG and GC, we will again consider the triangle ABG and GBC. Let's go on to the another slide. Here, for finding AG and GC, this is our third step. See, I am explaining you in steps so you will remember in your exams also. So, in first step we used cos angle. In second step we used sine angle. Now in the third step, while finding AG and GC, we have to consider tan. Okay, what is tan? Then tan is nothing but opposite side upon adjacent side. So we will consider that only in triangles. So in first we will consider tan R is nothing but it is AG upon BG, and in second triangle we consider tan R is nothing but GC upon BG. So by first tan R, AG is equal to BG tan R. BG is nothing but the thickness of film. Again substitute BG as T. So we will get AG is equal to T into tan R. Similarly with GC, GC is equal to BG tan R. BG is again the thickness of film. Substitute it with T. You will get GC is equal to T into tan R. Now from this third step, we got AG and GC. So now we will substitute this in our equation number 2. I will show you what was our equation number 2. This was our equation number 2. AF is equal to AG plus GC into sin I. Okay. So as we have found out what is AG and GC, we will substitute it in equation 2. So AF will be equal to T into tan R plus T into tan R, the bracket closed, and we will multiply it by sin I. So AF will be equal to 2 times T tan R into sin I. So this finally we got what is AF. Now let's go on to another slide. Yes. Now this is the step where we have to substitute all the values which we have found out in step 1, 2 and 3. So AB and BC we have found out, then AF we have found out. So in first equation I have also showed the equation number 1, that is optical path difference, that is delta is equal to mu AB plus BC minus mu naught AF. So in this equation number 1 we have to substitute the values. So delta will be equal to mu. What is AB and BC we have found out. We have written it. See what was it. It was T upon cos R plus T upon cos R. This is value of AB and BC minus mu naught AF. AF value we got 2T tan R into sin I. Again the value of mu naught. What is mu? It is refractive index, and the mu naught is refractive index of air. So refractive index of air is nothing but 1. So just keep it as 1, and then delta will be equal to 2 times mu T cos R minus 2T tan R into sin I. Okay, till this step I hope you have understood. Now concentrate more. Delta is equal to 2 mu T upon cos R minus 2T. Now we all know what is tan. Tan theta is nothing but sin theta upon cos theta. Similarly, here tan R will be equal to sin R upon cos R. So substitute in the place of tan. We got sin R upon cos R and the sin I, which is as it is. Now multiply and divide the equation by sin R. You will get to know why we are doing so. Because we have to get sin I upon sin R, which is nothing but mu according to Snell's law. So 2t into sin square R, because we have multiplied with sin R and divided by sin R. So in the numerator we got sin square R, and in the denominator we got sin R and cos R. So this is the equation which we got. So again I will explain you what I had did. I had just replaced tan R as sin R into cos R. Sin I is as it is, and then I have just multiplied and divided by sin R. So in numerator I got sin square R into sin I, and in the denominator I got sin R into cos R. I have did this because for just getting sin I upon sin R, for replacing it by mu, that is refractive index according to Snell's law. So here I have replaced sin I upon sin R by mu. So I got delta is equal to 2 mu T upon cos R minus 2 mu T into sin square R upon cos R. I am just simplifying and going further. Nothing complicated. Delta is equal to 2 mu T upon cos R. What I did in the second step, I just took 2 mu T upon cos R common from the equation. So I will get in the bracket 1 minus sin square R. Now by the first trigonometry identity, we all know sin square theta plus cos square theta is equal to 1. Similarly, we all know 1 minus sin square theta will be equal to cos square theta. That same thing we will apply over here. Then delta will be equal to 2 mu T upon cos R into cos square R. Just by cancelling cos R, we will get the final equation, that is delta is equal to 2 mu T cos R. Now, the main point, that is, as light is getting reflected from denser medium to rarer medium, that is from thin film to the air, so the path difference of lambda by 2 will be introduced because of Stokes law. So the total path difference will be delta is equal to 2 mu T cos R plus minus lambda by 2. This is our final equation for optical path difference. We have introduced lambda by 2 because the light is getting reflected from denser to rarer, as from thin film to air. So we have to introduce this lambda by 2. Okay, so this is the total optical path difference. Now we have to see the condition of maxima and minima. So for the condition of maxima, what is the value for delta? It is the even one, that is 2n lambda by 2. You can also take it as n lambda. Here I am taking 2n lambda by 2. So what delta we found out? Delta is nothing but 2 mu T cos R plus minus lambda by 2. That is our total optical path difference, which we have found out now itself. So that we will substitute over here, which is equal to 2n lambda by 2. Now we will take plus minus lambda by 2 from left to the right hand side. We will get 2 mu t cos r equal to 2n lambda by 2 plus minus lambda by 2. From here we will take lambda by 2 common and we will get 2 mu t cos r is equal to 2n plus minus 1 into lambda by 2. This is the condition for maxima. Remember these formulas, you have to remember because these are directly used in our numericals. So remember these formulas by practicing. Now we'll go to the condition of minima. In condition of minima, the delta value is odd one. So 2n plus minus 1 into lambda by 2 is the odd value that is given to delta. We all know what is delta, which we have found out. It is nothing but 2 mu t cos r plus minus lambda by 2. It is equal to 2n plus minus 1 into lambda by 2. Again by multiplying lambda by 2 inside the bracket, we will get 2n lambda by 2 plus minus lambda by 2. So on both hand side we have lambda by 2, lambda by 2, we will cancel it. We will get the final equation as 2 mu t cos r is equal to n lambda. So this is the condition of minima. Remember this formula as we have to use it in numerical. I am saying it again and again. Now the last for in transmitted light. What is transmitted light? It is nothing but the light which is neither reflected nor refracted. Okay, so delta for it is 2 mu t cos r. Now we will have the question why I have not introduced lambda by 2 over here. The reason I have written next on the line, that is as light is transmitted, no phase change occur. When the light gets transmitted, no phase change occur. Therefore, I have not introduced lambda by 2. In reflection and refraction, phase change occur. Hence, I have introduced lambda by 2. Now here, our delta is nothing but 2 mu t cos r. Now we have to find out the condition of maxima and condition of minima for the same. Here, the cheat sheet, what I have to say to you is the condition of maxima which is there in transmitted light is nothing but the condition of minima in our last concept. Okay, so here only interchange has taken place. Delta is equal to 2n lambda by 2. That is the condition of maxima. It is fixed. In before also we have used the same concept. So delta is equal to 2n lambda by 2. Just as delta here it is 2 mu t cos r, we will substitute it, which is equal to 2n lambda by 2 over here. And in condition of minima, delta is 2n plus minus 1 lambda by 2. So 2 mu t cos r will be equal to 2n plus minus 1 lambda by 2. Only simple conditions of maxima and minima in transmitted light. So I have covered all the concepts of this derivation. So I hope you have understood till now. So that was the interference in thin film of uniform thickness. In our next part of the video, learn what is interference in thin film of non-uniform thickness. This video we have covered uniform. So in this next video we will understand what is non-uniform thickness interference. So I hope you have understood the derivation. The total derivation comes in exams for 6 to 8 marks. So be thorough in the derivation. Learn the diagram, practice the diagram, consideration part, then what all steps I have explained you, step 1, step 2, step 3, where you have to take cos, sin and tan, I have explained you. So see the video twice or thrice till you understand. So for now, thanks for watching, and if you have not subscribed my channel, subscribe it, and if you like the video, hit the like button.